Okay, we're back. This should be the last lesson for chapter 4 for what I'm doing. So we're being very selective here. So what we're doing now, I'm going to stand behind so you can kind of get the notes down. There's not a ton of notes. I think this is almost the last slide. I'm just going to make a few comments here. So the topic we're doing here is, so acid waterways become acidic. Fine. Some systems, aquatic systems, soil systems, are better at holding on to a specific pH, which affects everything about the ecosystem, by the way. So much of the ecosystem depends on pH, just like the systems in your body depend on holding a specific pH. And the ability of a system or a substance to hold on to its pH is called the buffering capacity. So a buffer is something that resists changes in pH. So sorry, I'm waving this around. I'm not going to copy that definition down. And I put just an interest question here is which area of the country would be the most or least susceptible to acid rains? I'm just going to leave that as a question for you to look at that graph, which I can't really show very well on this printout. But I want to go through a little bit of the chemistry for what are some natural processes for how soils neutralize acid rain, if you will, or just acidic precipitation. And then also for what can we do as human beings to, well, neutralize excess acid if it's starting to cause trouble. And I'm just going to do this selectively. So I'll do my best here, because like when I do these things selectively, I kind of bounce around a bit. And there actually is a bit of chemistry and math involved that will set up a preview of coming attractions when we get to aquatic chemistry. I know I keep saying that every lecture, where we'll also have to take into account not just the water, but the soil and the minerals that surround it. And we're going to focus on the primary ones. Okay. So where am I now? And so buffering capacity is the ability of a substance. I'm just going to flip over to this graph here. I'm not going to explain this too much. I had some summer research students a couple summers ago when I first started to put this course together, and they went out and measured the buffering capacity of various aquatic systems. Well, how do you measure buffering capacity? Well, you take a sample of water and you basically titrate. You take hydrochloric acid using very low concentration, add it, and measure the volume of acid it takes to change the pH. The slope of the line, you can see that graph there, the slope of the line is the buffering capacity. If it has a high buffering capacity, it doesn't change the pH very much and it's kind of flat. If it's not very good at holding its pH, like if you did this with tap water, the pH would drop like a stone because it does not have much buffering capacity. But it depends on where you live. It depends on how the water is treated. Is it treated water? Is it well water? Is it, okay, you get the idea. So that's just a graph to show you some of that. I just tossed that in there because the students that did that research were in the class for the first time, and they actually stood up and explained their research a little bit. Okay, let's do a little bit of chemistry. I don't think I have much more to say about the slides, but I'll get to it. I'll look at it later. Okay, so what is this under? This is under natural soil neutralization. So we'll do natural, then we'll do anthropogenic. Okay, so this is the natural part. Hopefully this is right. So this is, I think, 3B. That matters for your notes. Soil neutralization. And it's complicated. It depends on what it is you're talking about. And this is where I have to bring in a little bit of language of geology. I thought bedrock was actually a specific mineral. Bedrock is just kind of a catch-all term. Just for what the rock that underlies the surface, I think. If some of you are geologists, you can correct me on that. So limestone, bedrock. What is limestone? Well, there's a lot of stuff in limestone, but the one we're most concerned about, is calcium carbonate. You might say, well, that's kind of looks like that has a piece of carbonic acid in it. Exactly. But it's not an acid. It's carbonic acid without the H. So it's a base. Okay, we'll get that. So if you take bedrock, limestone bedrock, that consists largely of calcium carbonate, and you put that in the presence of water, it will dissociate into calcium. If you look at the periodic table, calcium is in group 2. When it forms an ion, it will form a +2 cation. If that's stuff you need me to remind you of, I will. And that will now be dissolved in water, and then you get carbonate. So I'm pretty sure we've talked about that before. Dissolved in water. Fine. So let's also write that down. Carbonate. So you have carbonic acid, H2CO3, bicarbonate, HCO3 -1, and then carbonate, CO3 -2. And that's an interesting ion. Oh yes, by the way, no, we're not going to get to that now. You might remember, I don't think I'm going to do this. Yeah, okay. I was going to do that later, never mind. Carbonate, there's no acidic properties there, but carbonate can actually, act as a base. Now, I should be more precise. What I'm using, definitions of acids and bases, I'm using the Bronsted-Lowry definitions of acids and bases. So a definition of a Bronsted acid is something that yields H+. That's the same as any definition of an acid. The Arrhenius definition is what we usually assume. An acid gives H+, a base gives OH-. Those are what are called the Arrhenius definitions of acids and bases. A better, more comprehensive is Bronsted. Bronsted acid yields or gives up, produces H+, a Bronsted base takes in or absorbs or with H+. So that's exactly what happens. This is a Bronsted base. That will react with the acid that's in the environment, wherever it comes from. We talk about all the different places where that can come from. And that will then set up an equilibrium with bicarbonate. Now that's not a Ka, that's a Kb, a base constant, just so we know. So this is bicarbonate, just to use the vocabulary. This is then the conjugate acid. Go back and review this if you need to. So you have a base reacting with acid to produce so this is called a base conjugate acid pair. If I did it reversed, it would be an acid conjugate base pair. But we'll get used to that. And then the HCO3- can further react with more acid to go back to something we've talked about. That's carbonic acid. So this would now be acting as a base, which is interesting because we called it an acid before, but that was a conjugate acid. This is now acting as a base. Conjugate, sorry. Now, why am I doing this? Okay. What this shows you is that if you have a source of carbonate in the soil, in limestone bedrock, one great place to think about that is the Cumberland Valley where I'm currently standing. We have a limestone heavy area for soils, particularly in the Cumberland Valley and down towards Lancaster, which is one of the reasons why it makes it for good soil, because it doesn't change its pH, it's very resistant to that. This is some of the chemistry that gives things their buffering capacity. It's the ability of carbonate to absorb, if you will, H+ through these two chemical equilibria. And I'm sorry, I didn't write that as an equilibrium, that's terrible. And that's also a base constant. So in this case, we'd actually have Kb1 and Kb2. It comes from the same system. We are going to revisit this in the next chapter. Okay, Again, since I'm kind of being selective here, I'm bouncing around a little bit, but that's normal, sort of natural soil. Yeah, okay, sorry about that. I have to look at my notes on what exactly I had here. Now, okay. That's one thing you can do. I'm also add this here, sorry. I'll also introduce this equilibrium as well. Because when we get to water chemistry, we're going to have to take into account, I think 3, 4, maybe even 5 different chemical equilibrium expressions at once and slap them together chemically and mathematically. So I'm introducing the concepts now. So calcium carbonate, when it dissolves in water, it's not 100%. In fact, I should have written this one as an equilibrium. So you have an equilibrium in the presence of water between the solid calcium carbonate and its constituent ions. How much it dissociates is what's called a solubility product equilibrium constant. So solubility product. It's the same idea. It's the products, concentration of the products, divided by the concentration of the reactants, except in this case, this is a solid. There's no concentration molarity. It doesn't make any sense. It's not dissolved. So that's not included in the equilibrium expression. I'm just giving this concept right now. And like any equilibrium constant, you would look up the chemical formula, you would look up the temperature, you would look up the solvent, and what value does it give you? In this case, it's 8.7 times 10 to the negative 9. The units there would be molarity squared, but I'm not overly concerned about that. This is just introducing the concept. So that's called a KSP. So we need to take into account acid-base chemistry, but also solubility chemistry. How much of these ions get put into the water, and then subsequently, how do those ions react, in this case, to maintain pH and what's called buffering capacity. There's one other example I have here for what you also see in the ground. I'm kind of doing this last part combined. Because what happens naturally is the punchline of what we do anthropogenically to take care of acidic deposition. So calcium carbonate is just one example. Calcium oxide is another one. If you've ever dealt with cement before, this is often referred to somewhat informally as quick lime, okay? And that actually doesn't just dissolve in the presence of water, that reacts with water to produce calcium hydroxide, which maybe rings a bell because hydroxide is, well, OH minus, the opposite of an acid from the Uranian standpoint. And that's called slaked lime. These are just sort of historical definitions that have been used. What's the point here? Once you produce slaked lime, then you get a solubility setup. In the presence of water, you get calcium plus 2 ions. Oops, I'm going to the math, skipping the chemistry. So that's calcium plus 2 hydroxide ions, which makes something basic. So what's the point here? Is when you have calcium oxide in the presence of water, you get calcium hydroxide, slaked lime, which produces hydroxide, and that will neutralize H+, kind of like the carbonate and the bicarbonate neutralize the H plus by removing it and turning it into something else. That's the whole point of neutralization, is it reduces the amount of H plus. So the OH minus will do that as well. And then of course we have a KSP expression for this. Again, just to set up the math for future reference, it's the calcium ion concentration times the hydroxide ion concentration, in this case, raised to the second power because of that 2. That's called the law of mass action. I'm going into back into that theory. And the last one I want to mention, okay, just so we're not confused here, what are we doing here? The section where it says anthropogenic neutralization. Well, how do you not have soils get too much acid in them? Well, step one, there's nothing to add there. Just don't put as much stuff into the air. SO2, NO, NO2, well, that's coming, oh, duh, okay? Other things you can do, especially if it's a lake, this was a big thing in the Adirondack region of the New York State, is they were having acid rain problems back when I was in high school, and they actually took limestone from the Midwest and dumped it into a bunch of the lakes. You can add limestone, which we already have here, or slate lime, and that's a way of reducing the acidity of a natural water system. Just add it in. And that's a big thing that's done. There's lots of different ways to do that from an engineering standpoint. The last thing it says there is add phosphate. A very common procedure is phosphate can actually neutralize acid. I'm only going into this in a little bit of detail because it's kind of complicated. So I'm going to write this one out and only sketch the chemistry. So, sorry, this is 3B number 3. Or sorry, 3, yeah, it doesn't matter. My notes are all over the place, but there's not that much on the slides. So it doesn't really matter where you put them on the slides. That's phosphate. Why would you add phosphate? What would that possibly do? What is that? What would that do? Well, it's fertilizer. Some of these solutions are very practical. They're not getting down into the actual chemical equations. They're just like, well, they're practical solutions to these problems. So phosphate stimulates plant growth. It's plant food. If you have any kind of plant food or any kind of fertilizer, don't look at it. It's going to have a lot of phosphates in it. I'm not a botanist. That, folks, is an ion we're going to want to remember. Nitrate. Anything that contains nitrogen, any organic matter, any pollutant that has nitrogen, when it gets into the environment, that is the end of the line. So nitrates are one of the most important things that we measure, especially in an aquatic system, to get a gauge on the health of that water system. So this is a place for me to introduce this now. So if you stimulate plant growth, plants then uptake nitrates, and what does that do? And this is an interesting reaction. I don't think I'm going to balance this one. This is actually a reduction reaction. I'm not going to, you can do this yourself if you want to. I'm giving you the answer. This is 2 NO3s. So this is a reduction reaction, right? It's gaining these electrons. So I'm only showing you a half reaction here, because the point of this one is not to do the balancing. The point is this: once you get nitrate into the environment, it will be reduced in an acidic environment. That's what we're talking about here. So if it's an acidic environment, it will react with the nitrate. You have got 10 electrons, and it produces nitrogen gas, which effectively neutralizes the H+. This is a very efficient way of reducing the amount of acidity in the environment. Get more plants to grow. What does that matter? If you get more plants to grow, they uptake the NO3, and this reaction occurs, and you produce nitrogen, and you've now removed the H+ from the environment. That is simply another way of reducing it. That's more dependent on biology than it is chemistry. And I think that is it. Let me just check the slides. Oh, the last slide I had there was kind of an interesting graphic. You don't have to bother with this one. Is just sort of what, when you look at a type of bedrock, what are we talking about? Limestone, granite, what are its components? I'm not going to go through all of those. That was just there, just kind of, that was an interesting graphic. Oh, yeah, sorry. Eutrophication, I think we come back to this one, is if you have excessive nitrates, we are going to come back to this one. It's a good place to put this word, though. When you have excessive nutrients, nitrates, phosphates, fertilizers, dead decaying matter, and it goes into a system, and you can see the graphic there, is you then eventually deplete the oxygen from that atmosphere, from that environment, and that's called eutrophication. You get excessive plant growth, which can then kill other things because they are, well, preventing them from living. So this is what I want to put there. And that picture that I showed you there, sorry for the mild profanity on the slide, didn't spell it out, is a picture that I took down near the Chesapeake Bay where algal blooms were really taking over and wreaking havoc. Okay, so that's just a good vocabulary word for now.